Now let's talk about the other registers. RBP, which is the base pointer register, and again it's addressable as 64 bits, 32 bits, or 16 bits. Right, so what is the function of the base pointer? It points to a memory location in all versions of the processor for memory data transfers. So when we are talking about the memory data transfer, it is used to refer to an offset of a memory location. We'll look at that point in later on. Then again RDI, destination index, and again this is point needs no introduction. It often addresses string destination data for the string instructions. Remember I told you that DI has a combination with the ES. So when we carry out string instructions, so DI is referred along with the ES or extra segment register for the generation of a 20-bit physical address. Remember I told you 16 bits of segment address combined with 16 bits of offset address would generate a 20-bit physical address in the original Intel family. Source index addresses string source data for the string instructions, but also uses a general purpose register. So like DI and SI are all also general purpose registers, and they are also special registers for string instructions. So you can say that SI and DI are multi-purpose registers, general purpose registers as well as specific function registers. So as I talked about DI, when I talk about SI, I told you that SI is used in combination with DS. So we can write something like this: 16 bits of SI combined with 16 bits of DS would generate a 20-bit physical address. And this is the same, right, that we have discussed before. Now let's talk a little about special purpose registers. One of the most premier register is the instruction pointer register, and RIP, rest in peace, is basically a 64-bit version of the instruction pointer. And what is the function? It addresses the next instruction in a section of memory defined as the code segment, right? So like I have been talking before, when I talk about a physical address of a code, I would talk of these two addresses, right? 16 bits of IP combined with 16 bits of CS would generate a 20-bit physical address in the original 8086 processor, right? So this discussion that I have done before of DSSI, CSIP, ES and DI, these are all related to the original 8086 family, right? So this register is 16 bits when the microprocessor operates in real mode, and we'll talk about real mode and protected mode. Real mode is the original mode of operation of 8086. Real mode is a single user instruction. So sorry, single user mode of operation. And 8086, 8088 and 80286 do not contain an EIP register, right? EIP would be 32 bits, remember? So since these architectures are not true 32-bit architectures, the 80286, 88 and 8086 do not have EIP, they only have the IP register, which is a 16-bit register. Again, continuing our discussion with special purpose registers, RSP, stack pointer. And as we can see, everyone is aware of the stack, right? LIFO. So stack is managed in the microprocessor by using the stack pointer register and stack segment register. So like all other addresses, when we talk about the original 8086 processor, the combination of SS and SP generates a 20-bit physical address. 16 bits of SP the 16 bits of SS generates a 20-bit physical address. And basically if we generate a 20-bit physical address, let's say this is the physical address, right? So this physical address would definitely be pointing to the top of the stack. We will say that the top of the stack is at this physical address or physical, this should be PA, physical address. And how this physical address will be calculated? 16 bits of SP and 16 bits of SS. Again, we talk about a very important register, which is the flags register. Flags indicate the condition of the microprocessor and control its operation. So flags are used to communicate status as well as control the processor. So flags which generate the status or which indicate the status are known as status flags, and flags that control the operation of the processor are known as the control flags. And as we can see, there are a couple of these flags over here. This is the original flag register found in the baseline processors 8086 and onwards. So in the 280, 286, these additional flags were introduced. In the 386 and 486 processors, we can see these additional flags. And Pentium and above and core processors have this 21 bits of flags. So I told you the flags indicate the condition after an arithmetic and logic instruction, right? They only change as a result of arithmetic and logic instruction, and they are used in jumping or branching flow control, right? So let's say if we get a negative result, so the sign flag becomes 1 for negative result. Similarly, if the result is positive, the sign flag is 0. Remember, I already discussed about the 0 flag previously. If 0 flag is 1, what does it indicate? A 0 result. And if the 0 flag is 0, it indicates non-zero results. So there are a lot of flags, and they are usually used to indicate the result of an arithmetic and logic instruction. So what do? The general operation or general approach in branching in assembly language is to use the flags for branching. For example, if we carry out an arithmetic instruction, for example, we carry out an add instruction. Then we execute something like jump if 0 result underscore 0. And if the result is not 0, we go to the next instruction. So this is basically how branching occurs in assembly language. You carry out an arithmetic and logic instruction, and as we saw that arithmetic and logic instruction will change the flags, and then we'll check if the flag is set. If we want to make a decision if the result is 0, we carry out the jump if 0 instruction. So jump if 0 would check the 0 flag. If the 0 flag is 1, which means the result of this add operation was 0, we'll go to this label, which is R underscore 0. If the result is not 0, the 0 flag would be clear, or 0 flag would be 0. So this would be false. We won't go to this label, we go to the next instruction. So this is how basically branching can be performed. Let's have a little roundup of number systems, and we'll look at the binary number system. Binary number system uses a base of 2, right? This is something that we've already discussed. Right, so this is an example of the previous discussion that we have been having, number system roundup. So we are discussing about the binary number system, and binary number system uses base 2 and it uses positional notation. So what does this mean? We can take a straight example just to make things clearer, right? Let's say we have this number which is 1110.101. So we want to convert this number from binary form to decimal form. So how can we do that? We can use the positional notation. And what does the positional notation say? That values to the left of the decimal point in this direction, right, they begin with powers of 2 raised to power 0, 2 raised to power 1 and 2 raised to power 2. So the weight of this point at the left of the decimal is 2 raised to power 0, which is 1. Of this point is 2 raised to power 1, which is 2. And at this point it is 2 raised to power 2 is 4. What about to the right of the decimal point? The values are negative powers, right? So this digit would be 2 raised to power minus 1, which is 1 over 2, which is 0.5. This would be 1 over 2 raised to power 2, or 1 over 4, which is 0.25. And this would be 1 over 2 raised to power minus 3, or 1 over 8, or 0.125. So let's say what this number 110.101 would be in decimal system, right? So we'll see the weights, and we'll apply the weights by the binary digit, right? So over here it is 1 multiplied by 0, which is 0. It is now 1 multiplied the weight 2, which is 2. It is 1 multiplied by the weight 4, which is 4. So what are the values to be added to the left of the decimal point? 0 plus 2 plus 4. Now similarly, let's look to the values to the right of the decimal point. It would be 1 into 0.5, which is 0.5. It would be 0 into 0.25, which is 0. And it would be 1 into 0.125, which is 0.125. So what are the values to the right of the decimal point? 0.5 plus 0 plus 0.125. So when you add all these numbers together, this is 6.625 is the decimal equivalent of the binary number 110.101.